So we got the intuition that sometimes it's better to have an approximated, faster version than a more complex, more accurate. Linearization means approximating. So I think that everybody saw Taylor series. I think you heard about linearization before, true? Let's see it from a graphical perspective what linearization means. I have this function, there is this function, and then I've got a point. At y bar, I get f y bar, and I might linearize the function around this point here whenever basically I consider the derivative of that function evaluated there. True? This one we know. Okay? And we can say that eventually the linearized version is an approximation. And it's as good as a better approximation if we are working around here. If we are working around here, this one and this one, there's a bigger error. True? This is very, very, very basic. Okay. To compute this approximation, this one might exist. Watch out that this is a common mistake. If I have, for example, a function that looks like this one, or better, this one, and this is my f, I can't linearize around here together. Okay, so it's not given that I can linearize always. Okay, another example, if I've got a function that looks like this one, and here I've got a discontinuity, also there I cannot linearize. Okay, so it's not guaranteed that I can linearize together. Perfect. Whenever I go higher in dimensions, linearizing means linearizing every component. True. If I have a function that looks like this one, y1, y2, and I have a function that looks like this one, linearizing around here means finding a plane. You see it? Okay. And if you think at Lotka Volterra, how many blankets do we have? Two blankets. True. For every dot, every y dot, every one dot, y1 dot, y2 dot, y3 dot, y4 dot. True. For every yn dot, I will have a blanket, and I will need to linearize. I didn't say it in a good way, but you got the point. Whenever I have more variables, I need to linearize every variable. Perfect. I need to have a matrix. Let's make an example. If I have a function that takes, if this one is a vector of dimension 4, if the y0 is a vector of dimension 4, this one is going to be a matrix of dimensions 4 times 4. True? Perfect. Some exercises, if you don't remember how to linearize, do the exercises that are in the slides. The procedural part, I assume that you are able to do it. Okay, matrices of opportune size. Let's go here. There is an important thing. Are we together that whenever we take a point here and a value here, it means that I want to approximate with a plane? We are together on this? This one would be basically the value that is the offset plus a derivative. Let's make it, let me rewrite it. This component here would be alpha times delta x plus beta times delta u, or delta y, sorry. I do not know why I've got x. Is it x? There's a typo here. This alpha would be what? The derivative, this angle here. True? You see? The derivative with respect to y. This beta would be what? This angle here. Together. And of course, we take delta y, delta u in the sense of delta y and delta u. We are together on this, true? We remember this stuff. Perfect. Let's go to something that is important. If I linearize an ODE, it means that I am linearizing the dynamics. Now the interpretation. So the previous part is functions, linearizing functions. I think you remember. If you do not remember, recheck. It's just approximating functions. Now, whenever we approximate an ODE, the animal, so we are moving from linearization of functions to linearizations of ODEs. Linearization of ODEs, different animal. Very different animal. Because from a conceptual perspective, things are very different. Let's make an example. So this is non-linear and this is linear. Perfect. Let's go here. I might have messed up with the visualization. I think I removed by mistake a drawing, but I do it here. And I will put it back here. Let me show you this example here. Y dot Y and this is my Y dot. And I want to linearize around here. What is my linearization? My linearization around there is going to be something that looks like this one. True? See? The problem with this approximation here is a problem that whenever we do this approximation, we are affecting the forecast in the future. And it might be a dramatic change of the forecast in the future. If I start with this initial condition here, and this one, blue, is the true model, and this green is the linearized model, given the true model, where do I go? Right or left? Right. Given the approximated model, where do I go? Right or left? Left. You see that somehow linearizing an ODE will affect the trajectories that you generate. So the linearization is not just a linearization of a function, but it's a linearization of all the trajectories of the system. The effects might be dramatic. Tomorrow we are going to see better. We see each other tomorrow morning at 10:15 to do the labs. Come prepared. Python installed, okay?